Hello everyone, we have been discussing the vapor pressure and the effect of salt content in water, the effect of salt presence in water on vapor pressure we have briefly seen towards the end of the previous lecture. And as we understand that the effect of salts in water on vapor pressure, it lowers the humidity when you have salts in pure water. When you add sodium chloride, when you prepare a sodium chloride solution, when it compared to the pure water, the vapor pressure drops, because of which the relative humidity decreases. So therefore lower humidity is experienced near seashore compared to places near larger river bodies at the same temperature. So here the example is given. If you compare the relative humidity in Chennai and Guwahati in summer, but it should be compared at the same temperatures. Chennai, it can be as the temperatures could be as high as 45 degrees, 46, 47 degrees Celsius, but in Guwahati you won't experience more than 40 degrees Celsius. So therefore a direct comparison may not be possible, but at the same temperature, if you compare Guwahati, which is the places where you are next to the Brahmaputra river, a huge large water body, you experience more humid climate. As we have seen in the previous lecture, when the relative humidity decreases, you experience drying of your body, because the sweat is taken by the atmosphere. There is a mass transformation that takes place, and the sweat is taken by the atmosphere when the humidities are low, and as it hasn't reached the saturated vapor pressure, it can take more and more sweat and you feel dry. So you feel thirsty very often when you are sitting in air conditioned room or in dry climates. On the other hand, if you are in very humid places, so the body sweat is not taken by the atmosphere, because of which the body temperatures increase. If the sweat is taken by the atmosphere, due to the latent heat mechanism, the body temperature cools down. But when the sweat is not taken by the atmosphere, then the body temperature keeps increasing. That is dangerous. The body temperature increases with the atmospheric temperature. That is dangerous. So similarly, the soils experience such kind of variations with the changes in the humidity and temperature environments as our body experiences. So if you keep a soil mass outside in the atmosphere, you would see that the moisture is absorbed by the atmosphere, or evaporation takes place. The evaporation takes place until there is a chemical equilibrium between soil pore and atmosphere. So the chemical potential of the soil pore should be equal to the chemical potential of the atmosphere. Until then there is a mass transformation that takes place, mass transfer that takes place. So this is very much important, which we often experience with simple test also, that is shrinkage limit test. In shrinkage limit test, we evaporate the water until the volume stops changing, then we determine the shrinkage limit. So this shrinkage limit or volumetric shrinkage behavior, that is volume of soil sample to the mass of soil sample, it again varies with the atmospheric conditions. So another important point is that the presence of salts also alter the boiling point and freezing point of water or ice. So for example, there is an example, this may not be the exact values, but if you add 10% of salt in water, the freezing point can change to -6 degrees Celsius. So if you add 20% salt, the freezing point can change to -16 degrees Celsius. This is one of the important mechanism why we use salts in cold countries to melt the ice. When the ice is deposited near your apartment, we generally put rock salt, so that which has a good concentration of NaCl, and because of this salt addition the freezing point changes, so therefore ice melt down. To understand the phase changes, often you see that there is a change in the phase. Water becomes vapor and water can also become ice. And so there is a phase transformation that often takes place due to the changes in the environmental conditions. So the water can exist in three phases, one as a liquid, another one as gaseous phase, another one is solid phase. So but then at different temperatures, change in the temperature or pressure can cause a change in the phase transformation takes place. For example, for pure water, when the temperature increases, you have a water at this particular temperature. When the temperature increases, it follows ideal boiling path and it becomes vapor. At that particular temperature, 100 degrees Celsius, so it becomes at the atmospheric conditions like 101.325 kilopascal, it's absolute pressure. Then when you are boiling, when the temperature reaches to 100 degrees Celsius, it boils and water becomes vapor. Water also becomes vapor at a constant temperature, but when the pressure is decreased, which is called cavitation. So often you see when you have a beaker, so beaker of water, this is water, so this is connected to a pump exerts a vacuum, connected to a vacuum pump. When you operate this, so the pressure inside drops. So at the 20 degrees Celsius itself, you see that a lot of bubbles would form and water starts to boil. So this is cavitation. So due to decrease in the pressure, the water bubbles, the vapor forms within the water, which is called cavitation. So this is a vaporization curve. This particular curve is a vaporization curve. So if water crosses this particular curve under given pressure and temperature conditions, it becomes vapor. And this is called sublimation curve, where the ice can become directly vapor without going to the water phase. So the solid phase can be changed to the gas phase directly through this phase transformation by changing pressure or temperature. This is often seen in soil mechanics, where you want to recover, when you want to test a soil sample, soil specimen, without altering its structure, without altering its particle structure, then what we do is we freeze dry the soil sample so that the water directly becomes ice, and after that we follow this sublimation condition where the pressure is dropped under a constant temperature. So then directly it forms vapor and vapor escapes to the atmosphere. You have the soil sample without changing its pore structure. Otherwise, if you follow this path where the temperature is dropped, when you freeze dry and then when your temperature is dropped, then it becomes water. Or for example, otherwise if you have a saturated soil sample, if you want to test its pore structure using some mercury intrusion porostometry or scanning electron microscope to observe the particle structure or pore structure, then it is not possible to dry the soil sample, because drying the soil sample alters the pore structure. So therefore often we freeze dry it and follow the sublimation, cross the sublimation curve and then make it to gas, and when the gas escapes you have the soil without altering its pore structure. That is how we test it. So this is a very important point, and this particular point is called triple point, where water can exist in three different phases. This point exists at 0.01 degrees Celsius and pressure is 0.61 kilopascal. This is triple point, or 273.15 kilo Kelvin and 0.61 kilopascal. So this phase change phenomena is very important in soil mechanics, especially unsaturated soil mechanics. Are many experimental facilities which determine or control the state variables such as suction, or directly or indirectly depend on these principles. They directly use these principles. So let us look at the dew formation or condensation. So this is this particular phase transformation we are looking at. So one of the important state variable measurement is matrix suction, or the suction measurement instrument called WP4 or dew point potentiometer is based on this particular principle. If you take, if you consider the present atmosphere, this may have a particular temperature and particular vapor pressure. So the particular vapor pressure may be, so that is UV, this is point A, so therefore this should be UVA. So this is at particular temperature T1. So at T1 the relative humidity RH is equals to nothing but UVA divided by UV sat, saturated vapor pressure. So at this particular point, this is the saturated vapor pressure. At this particular temperature, this is the saturated vapor pressure, and this is the vapor pressure. So RH is the ratio of relative humidity to the saturated vapor pressure. Vapor pressure at this particular point to the saturated vapor pressure at this particular temperature, that is RH. So when there is a sudden decrease in the temperature, keeping the vapor pressure constant, then it follows a cooling path. It follows a cooling path. Then you see that there is a formation of dew, or another path is possible where you increase the temperature, you keeping the constant temperature, you increase the vapor pressure, then it reaches the saturated vapor pressure. So either way it is possible to achieve dew point. This is often encountered, so where we see that there is a sudden decrease in the temperature that causes a formation of dew or condensation, and raindrops would fall. That is nothing but the atmospheric vapor gets deposited as dew. So this is a very useful expression to estimate the dew point temperature, knowing the vapor pressure, knowing the RH, or knowing the relative humidity. For example, RH is given, relative humidity is given, and temperature is given. So using this, you can estimate what is the dew point temperature. For example, say RH is equal to 90% and temperature is 40 degrees Celsius. So then RH is known, you know the saturated vapor pressure knowing the temperature from the Tetten's equation. So then you can estimate what is the UV. So knowing the UV, if you substitute, you will know what is the dew point temperature. So when the temperature drops to dew point temperature or below dew point temperature, you see that there is a formation of dew. So this is often we encounter on a car windshield. Car windshields often get fogged up, and we switch on the defogger for clearing the condensation. So this is because suddenly if the temperature outside it changes, then temperature drops, then you see that the condensation that happens inside the car windshield, and vice versa it may happen. So water vapor condenses on a surface if the temperature of the surface is below dew point temperature of the moist air in contact with the surface. Consider this example where you have, say, RH is equals to 50%, RH equals to 50%, and temperature is 40%, 40 degrees Celsius, temperature is 40 degrees Celsius. Then the UV is 3.694 kilopascal, and UV sat from the Tetten's expression is 7.388 kilopascal. Suddenly if the temperature drops to 20 degrees Celsius, then the UV sat for 20 degrees Celsius is 2.344 kilopascal, which is less than the current UV. So therefore it causes fogging. So your windshield inside gets fogged. Similarly, there is another phenomenon that we often observe is cavitation. I just mentioned that this is a cavitation path. cavitation happens. Cavitation is nothing but formation of vapor bubbles within liquid at low pressure regions. So as I just explained, when you have a water that is pressure is reduced by applying vacuum, then you see that the water boils or vapor forms, vapor bubbles form. The same thing we observe in traxial setup, where we have a soil sample, where we apply some all round pressure sigma 3, and we apply additional deviated stress sigma delta sigma. So when you are conducting a drain test, consolidated drain test, the pore water pressure generally, excess pore water pressure generally gets dissipated, and when you are not maintaining any particular pore water pressure inside, then pore water pressure may be 0, and then in that particular case you see that sample dilates if the initial compaction state is such that the soil is over consolidated clay or densely compacted sand, and soil dilates. However, if it is a consolidated undrained test where the drainage is not allowed, water is not allowed to go inside the sample or outside to the sample. So in that particular case, the changes in the pore water pressure, if you observe for the over consolidated clays with axial strain, change in axial strain, you see that there is a change in the pore water pressure, which is actually there is a negative pore water pressure that develops. So this is in particularly for densely compacted sand or over consolidated clays, where the negative pore water pressure develops, because when you consider particles to be of spherical in nature, and particles are compacted well because this is a densely compacted sand, when you are shearing this top layer, so particles have to climb up the bottom particles, because of which it wants to suck the pore water, it wants to suck the water to fill in the gaps, but however the water movement is not allowed, therefore there is a negative pressure that develops. Because of the development of the negative pore water pressure, which causes formation of bubbles or cavities will form or cavitation occurs. So to avoid that, often we maintain a particular back pressure. A back pressure equal to some UH is often maintained. If back pressure of 100 kilopascal is maintained, then cavitation would not occur, because when the negative pore water pressure develops, which compensates the back pressure, compensates that whatever the negative pore water pressure that develops in the sample. So these concepts are very much relevant to even basic soil mechanics, but you would see many more application of the cavitation phenomenon in unsaturated soil mechanics, especially in the application of tensiometer. Tensiometer is one setup for measurement of suction. A state variable in unsaturated soil mechanics. As we have seen that water can exist as vapor in air phase. So in that particular case, the density of air changes. Earlier we have estimated the density of air using ideal gas law. So what happens to the density of air when vapor is present? So as we have used this particular relationship earlier using the ideal gas law, where the density of air is equals to the UA, the atmospheric pressure, times the molar mass of air divided by gas constant times the temperature in Kelvin. Here I said the molar mass has units of gram per mole or kg per kilomole. So in many textbooks they are defining, in many textbooks they are defining MA as molecular mass. They are defining MA as molecular mass, not molar mass. So but then molar mass is of a substance is the mass per mole of its atoms. So it has units of kg per kilomole. In contrary, the molecular mass is the mass of single atom. It should be measured in kilograms. Or if you want to use molecular weight or atomic mass constant is the relative molecular mass of atom, which is measured in atomic mass unit. It doesn't have, it's a dimensionless parameter. So therefore, usage of molecular weight or molecular mass is wrong, because first of all it's not dimensionally correct. It should be molar mass only, because when UA you substitute in kilopascal or kilonewton per meter square, then molar mass in kg per kilomole or in joule per Kelvin mole, and temperature in Kelvin, then this has units of kg per meter cube. This we have seen in the previous lecture, one of the previous lectures. Please make a note of this. So let us derive the expression for density of moist air. Assuming that the dry air and vapor follow ideal gas law, when we define rho dA, that is dry atmospheric air, that is equals to UA, atmospheric pressure, times MD, molar mass of dry air, divided by RT, and rho V is for vapor density, is equals to vapor pressure times molar mass of vapor divided by RT. So the moist air density is equals to, this is vapor density, this is density of dry air that is present in the moist air. So you are separately considering density of vapor, density of dry air that is present in the moist air. Then this is the expression you get. Here the density of dry air that is present in the moist air can be written as atmospheric pressure minus the vapor pressure. So then this expression can be simplified to this, where you can write UA times MD by RT minus UV times MD minus MV divided by RT. So this can be further simplified by multiplying with MV in the denominator and numerator and denominator. Then this MD minus MV can be written as this, and this MV times UV divided by RT can be written as rho V further. So this is simplified to rho dA, the dry atmospheric air, minus MD minus MV by MV times rho V. So therefore the expression for density of moist air is rho dA, density of dry air, dry atmospheric air. That means if you have completely dry air, there is no vapor that is present, then the density is this much, minus molar mass of dry air divided by molar mass of vapor. Molar mass of dry air is 28.94 kg per kilomole, we have used earlier, and molar mass of vapor is 18 kg per kilomole. So divided by MD by MV minus 1 times rho V sat times RH. The rho V is written as rho V sat times RH. So because from the relative humidity definition we can write rho V sat times RH. So where different variables are defined here, so it can be further simplified because rho V sat can be obtained from the Tetens expression. So from that we can write what is rho A moist, where you have UA, atmospheric pressure, and molar mass of dry air, and RT. So this is for a given condition, this is atmospheric condition, that is 101.325 kilopascal, MD is 28.94 kg per kilomole, R is 8.314 joule per Kelvin mole, and T temperature is maybe standard temperature, say 20 degrees, then it is 273.15 plus temperature 20 degrees Celsius in Kelvin, minus 0.611. This is again 28.94 divided by 18 minus 1, exponential of 17.27 times temperature in Kelvin, RH is required, and RT we know the substitution, and MV is known, which is 18. So from this one can estimate how the moist density changes with temperature, relative humidity and atmospheric pressure. First let us understand how the air density changes with relative humidity when temperature is maintained 48 degrees and atmospheric pressure is 101.3 kilopascal. So the relative humidity 50 degrees may simulate a condition of dry climate, maybe near Hyderabad or some places where you have a dry climate, and 90 degrees may simulate a condition of Chennai, close to Chennai environment where temperature can go to 40 degrees and relative humidity will be 90%. And this is near mean sea level, so this is pressure is 101.3 kilopascal. So in the first case, rho A moist is UA is 101.325 kilopascal times MD is 28.94 kg per kilomole divided by R is 8.314 joule per kg joule per Kelvin mole into temperature 298 Kelvin minus 0.611 times MD 28.94 by 18 minus 1 into exponential of 17.27 and temperature is 273.15 plus 48. So here the temperature is 273.15 plus 48 minus 273.15 divided by same again 273.15 plus 48 minus 36 bracket close times RH relative humidity is 0.5. Here it should be substituted in decimals, not percentage. So 0.5 times MV is vapor 18 divided by RT is 8.314 times temperature again 273.15 plus 48. So which gives a value of 1.09824. There is a density of dry air minus 0.0229, which is 1.0753 kg per meter cube. So eventually there is a decrease of 2.1% of density. So the density of moist air here in this particular case with relative humidity of 50% is 2.1% lighter than the dry air. So with increase in moisture, this particular value is corresponding to 0% RH, completely dry air. So if you substitute for RH equals to 0, then you get density of dry air. So therefore with increase in the RH, the density of moist air decreased. Though this value is very small, negligible value 2%, but then this plays an important role in the flow of air from one place to another place due to changes in the RH. Similarly, changes in the temperature also we will see very soon. So if I erase this whole part here, so corresponding to 50% of RH, when RH is 50%, when RH is 90%, would see that in this particular case the density of moisture is 1.0753 kg per meter cube, and with 90% this is 1.057. So the dry air is 1.09824 and 50% is 1.0753. 90% further decreases to 1.057. So with the decrease in the temperature from 48 to 20 degrees, so then the RH becomes 1.1979 when RH is 50%. This value is 1.1937 when RH is 90%. And when the temperature is maintained constant at 20 degrees, but atmospheric pressure is decreased to 80 kilopascal, then for RH equal to 50%, so this value is 0.9447 kg per meter cube, and at 90% RH this is 0.9405 kg per meter cube. So from this you can see that at a constant temperature and pressure, with increase in RH, the density of moisture decreases, because more and more moisture would go into the atmosphere. As the molar mass of vapor is smaller than the molar mass of dry air, more and more vapor goes into the atmospheric air, then it decreases the density of air. Similarly, when temperature decreases from 48 degrees to 20 degrees, you would see that there is an increase in the density, or other way around, when the temperature increases, which decreases the density of air under the same RH and atmospheric pressure. In contrary, at the same temperature and then RH condition, when the atmospheric pressure is decreased, the density of air decreases. So therefore, this in summary, the density of moisture decreases with increase in RH when temperature and atmospheric pressure are constant. Similarly, the density of moisture decreases with increase in temperature when RH and atmospheric pressure are constant, and density of moisture increases with increase in atmospheric pressure and when RH and temperature are constant. Thank you.